Hey everyone, so today I'm going to answer the question, why are hash maps ov1? And I have gotten this question before, so this video won't be on hash map theory. I'm going to drop a separate video on hash map theory in general, but I'm just going to quickly answer the question, why are hash maps ov1? And the best way to answer this is through an example. So let's work through this example where we have a bunch of names and we just want to store them in a data structure, and then maybe we want to ask if we have a certain we want to store them, and we want to later figure out which names we have stored in our data structure. So one data structure we can use is just a simple array. So let's just take all these names and then store them in a simple list. Let's say J, CFA, Nat, Alf, Liam, Paul. So now we have a list of names, and if we ever want to pretend we want to ask questions, is Liam in our list? Say we want to know if Liam's in our list. What we can do is we can do a linear search and look for Liam from left to right until we see Liam, and we can say yes. Pretend we're looking for something like Mia. Well, we can go from left to right and we won't see Mia in there. And yeah, basically we can return false. So let me go back. That's the simplest way to store the data in a regular list, but searching for an element is O(n) time. So one way that we could actually speed it up is, okay, let's store all the names, but keep all of the names sorted. So maybe so we can take all the names and put it in sorted order. So what would be the sorted order here? I think alpha definitely goes first, so alpha, and then CFA, then we go J, then we go Liam, then we go Nat, then we can go Paul. So now we store it in our list in alphabetical order. So how fast can we search this? Since it's sorted in alphabetical order, we could actually perform a binary search. So if we're looking for alpha, for example, we can look at the middle. We know this letter is, or this name is J. So we know alpha, since it's sorted in alphabetical order, we know alpha is probably to the left because it's in alphabetical order, it comes before J. And we know that we can disregard everyone here. So yeah, we can use binary search in order to find it, and that will lead to a log of n solution. But now we need to keep the array sorted. So pretty much pretend we want to add new people. Let's just put one as like Grogu. We put Grogu. Now where do we put Grogu? A, B, C, D, E, F, G, H, I, J. Probably somewhere here. So we'd have to put Grogu, but since this is a list, we'd have to pretty much put Grogu here and then move everyone over. And moving over people over there will be an O(n) runtime because we have to shift everyone to the right. So it slows down our insertions essentially. But if we did have it sorted automatically, we would be able to search for it in log of n time. Let me delete this. So yeah, these are the two solutions that I'm just walking through different ways we can store it. We can store data in a regular list. That'll be O(n) search time. We can keep the data sorted, and that would lead us to log of n time. But then it slows down our insertions because we need to keep the data sorted. And then finally, let's go to our most optimal way of storing the data, which is using a hash map, which is actually O(1) time amortized. And I'll talk about why it's amortized. But let's just say it's O(1) time for now. So a hash map is still actually a list under the hood, but when we go to store elements into the list, what we do is we take the element and we calculate the index of where we should place this element using a hash function. So what that hash function does is, yeah, it essentially calculates an index based on the element, and then now the element, where the element is stored, is now correlated to the actual value of that element. So instead of the first case where we just store data where we store data in the regular list based on when we've seen them, or we try to organize it and keep it in a sort order, what we do is when we receive a name, for example, we receive the name J, what we do is we calculate the index of where we should put J based on the actual name J. So one very basic way to do this is pretend we want to store J into our hash map. Let's take every single character and take the ASCII value of each character in the name, add them up, and then generate an index by taking the modulo of all of these ASCII values added up. We need to take the modulo so it actually fits into our array here, because pretend we get like 100. Well, we want to modulo it so that it fits in some sort of index. But yeah, this is a very simple one. Sum the ASCII codes of each element and take the modulo of the size of the array, and then that's how we generate the index. So what is the ASCII value? Well, ASCII value pretty much maps characters to numbers. So for example, we want to calculate the index of where J should go. Well, we take J. What's the ASCII value of J? Well, it's 106 right here. What's the ASCII value of A? 97. What's the ASCII value of Y? Where's Y right here? 121. So we add those up and we take the modulo 17 so it fits in the array, and then we actually get 1. So now we know we need to store J into 1. So we store J into 1 right here. Actually let's just do this. So we put J into 1. Now let's go through CFA. So now take CFA. C is 99. F is 102. A is 97 again. So now we add those up and mod by 17. And now we put CFA in 9. So you can see that we're being more smart of where we place these elements. And we're doing it based on the actual name. So now it's more correlated. So nat goes into 0 here. Alpha goes into 13. So I'll just say it again. What we do is we go through each one, take the ASCII value of each character and add them up, and that should produce us a big value like 421. And then we have to do a mod in order to make it fit within the array, and that 13 is the index we put it in. So this is essentially what the hash function is doing. Basically, it's something like what it would do is it's like a function where you just call the function on alpha, and under the hood it'll perform this. It'll capture the ASCII values, add them up, and mod it by 17, and then it should spit out 13. And then now we know, let's put alpha at 13 right here, or alpha at 13. Liam goes to 11. And then this is an interesting part. We calculate Paul, but now Paul has a collision with CFA. So what do we do here? Well, Paul should actually go also in 9. But then we see that 9 CFA is already there. So what we can do is have a linked list at every single element. And this is just one way to solve collisions, but have a linked list at every single element or every single index. And now we just have a linked list of CFA to Paul. So now I showed you how we insert into the hash map, which is essentially take the value and hash it, or take the element, the name, whatever you're storing in the hash map, and hash it to generate an index. Now store it in the index generated by the hash. If there's a collision, instead of storing in the next open slot, that's sort of open addressing. What we can do, if there's a collision, add to back of linked list. So this is one strategy. I'll talk about multiple. So if there's a collision, add to back of the linked list. That's what we did here. So how do we actually get values from the hash map? This is the part that's actually O of 1. So how do we do this? Well, pretend pretend we're looking for Liam, right? Where is Liam? Do we need to do a search, a linear search here, which would be O of n? Do we need to do a binary search? Well, we can't do a binary search because it's not sorted. What we do is we take Liam, when we pass Liam through the hash function, what it will do is add up all the ASCII characters. It'll perform the same calculation here of 108 plus 105, and then I forgot the mod here. The final value 419 gets mod by 17. So we passed Liam through the hash function and we should get 11. And now we look at the 11th index for Liam. And we see Liam is there and we could say true. So that's O of 1. Well, I guess it's actually O of like depending on the hash function. First off, the hash function needs to be fast. Otherwise, it defeats the purpose. But for here, if the names are fairly short, pretend all the names are under 10 characters, it would be pretty much O of 10 just to calculate this. And pretty much we dropped constant, so O of 10 is pretty much O of 1. That's why we're saying O of 1. But yeah, we just take the hash function or the hash of Liam and we generate 11. Now we just look at 11. We didn't need to search anything. We figured out the index by just running Liam through the hash function. That's why it's O of 1 hash map, and or O of 1 time complexity to search to find elements in a hash map. And why it's amortized is the main reason why we say amortize is because of collisions. So pretend we're looking for Paul. Well, Paul has the same index as CFA. So when we look into this index, it's a linked list. We see CFA is not there, but we see that there's other values or other names that share the same index after we apply it through the hash function. And now we essentially need to search the linked list in order to look to see if we've seen Paul already. So yeah, we pretty much do a linked list linear traversal to find out if we inserted Paul already. So that's why it's O of 1 amortized, because if you have a good hash function that distributes all of the names correctly, pretend we have a hash function instead put Paul here, then we wouldn't need to search through that linked list. So that's an important part, is being able to take the data and uniformly distribute it across the list. So yeah, if there's a lot of collisions, then it degrades the runtime and it's not O of 1 anymore. And if you have also the list size here. So if you choose a small list, pretend we want to store 50 names in a list of 17, then there's going to be collisions for sure. And that also degrades the runtime of the hash map. So all of those are key parameters to tune in order to have an optimal running hash map. And yeah, let me just go through the steps again. Like what I'll say is our hash map or our hash function that we introduced, which is summing the ASCII codes of each element and then taking the modulo, is not a good hash function because it doesn't uniformly distribute the elements well, because anagrams will get the same index. That's one thing. So yeah, like I mentioned, it should be uniform to reduce collisions. It should also be deterministic. That means given every time you pass in the value, you should get the same index. So if I put James and I get index 0, and I put James again, I should get index 0 every time I call the hash function on James. If it produces me a different value each time, that defeats the purpose, because then like when I pretend I call James and it produces me 5, then I'll look into the wrong index. So it should be deterministic, which means yeah, it should always give the same value. It should always give the same index given a specific name. And yeah, there's different ways to handle collisions. One way is through chaining, like I mentioned, and this is not a hash map theory video, so I'll get into chaining and open addressing in a separate video. So yeah, that's pretty much answered the questions. Why are hash maps O of 1? If you have any more questions, just reach out to me. I'm gonna have a video dropping soon on going more deep on hash map theory. And yeah, I just wanted to answer the simple question, or I guess it's not simple, but why are hash maps O1? It's because of this hash function that tells us exactly, that maps names or values into an index. So we could easily find the index of something we're looking for by running it again through the hash function. Yeah, thanks for tuning in. I'll see y'all in the next video.